It's amazing how much we can take for granted sometimes in today's world of modern technology. Take this example. You're barreling down the highway on your way to work, along with a few million other people in your metropolitan area. Suddenly, ahead of you, there's a car accident. Now, with equal suddenness, hundreds of cars weighing millions of pounds come screeching to a halt in just a few feet. Most of us have been in this kind of situation before. And when something like that happens, have you ever stopped to reflect on the fact that you just put a stop to 2,000 pounds of barreling vehicle with a tap of your foot? That's pretty mind-boggling, isn't it? How does that tiny little bit of force that you put on the brake pedal with your foot stop something as massive as a speeding car with such ease? Well, in this lecture, we're going to answer part of that question and others as we turn our attention to liquids. Our discussion in this lecture is going to cover some of the more familiar properties of liquids that we can observe in the macro-scale world. Specifically, we're going to talk about the properties of viscosity, volatility, vapor pressure, compressibility, and another one called miscibility. And although I'm sure you have observed examples of all of these many times in your life, what I hope to do in this lecture is inject a bit of insight as to what's happening at the molecular scale that endows many of the most familiar liquids from our everyday lives with their own unique sets of properties. Let's begin by refreshing ourselves on the most common intermolecular forces in pure substances. We have London dispersion forces, which are attractive forces based on intermittent dipoles. And these form as electron clouds flex and shift around molecules and atoms. Next, there are dipole-dipole interactions, in which permanent charge separations caused by differing electronegativities in their bonded atoms create an electrostatic attraction. Third, of course, is hydrogen bonding, that ever so tenuous bond that can form between molecules with an OH, NH, or FH bond within them. In gases, we often assume that these intermolecular forces are negligible, and that molecular motion, or their kinetic energy, is able to completely overcome them. And just like gases, liquids can experience all of these forces between and among the molecules and atoms that make them up. But remember, the defining difference between liquids and gases is that in liquids, all the molecules in the sample are in constant contact. And this is because in liquids, those intermolecular forces are too strong for the molecules to overcome. This is about as non-ideal of a behavior as you can imagine, right? Now, because of this, intermolecular forces in liquids cannot be ignored like they were in gases, even under the best of circumstances. So, our days of assuming that all samples will act exactly the same regardless of composition are well behind us. There will be no ideal liquid laws. Fortunately, we're already equipped with the knowledge we need to start rationalizing some of the properties that we do see in common liquids. So let's do that now. Let's begin today's task of accounting for the properties of liquids and how that close, intimate contact at the molecular level will affect their behavior. In this lecture, we're going to discuss just a few of the most important properties of liquids, properties that scientists and engineers have to carefully consider when developing and using new materials to improve our quality of life. Now, our first property is viscosity. Most of us are vaguely familiar with this property of liquids. Viscosity is best defined as resistance to flow. If I were to invert similar-sized bottles of water and motor oil, what would you expect the result to be? Well, of course, most of us would correctly predict that the bottle of water would empty out first, and the oil would pour out in a slower, lazier process. Now, the reason behind that is that motor oil is more viscous than water, and it resists flowing out of the bottle under the force of gravity, so it just takes longer to escape. Viscosity is a crucial property of liquids used in certain applications. From machine lubricants to magma in the Earth's subsurface to blood in your veins, flowing liquids are a part of nearly every natural or man-made system that we can study. So, what makes a liquid more or less viscous? Well, one obvious parameter is temperature. Most of us have heard the old adage, slower than molasses in January. Well, the January part of that remark is a reference to the effect of temperature on viscosity. Molasses obviously flows more slowly in colder temperatures, inspiring the cliché phrase. Remember that to a chemist, temperature means kinetic molecular energy. So lower temperature means slower moving molecules and atoms within a liquid sample. This tendency of molecules to move more slowly at low temperature means that they can glom onto one another more effectively under the influence of their intermolecular forces. This makes them more resistant to flow as they cool down. But there must be more to viscosity than just temperature. After all, we're familiar with certain vital products that have differing viscosities at the same temperature. Take the example of gasoline and motor oil. Gasoline is a very thin, easy-flowing liquid, which it has to be if it's going to do its job of being pumped easily through fuel lines into an engine like the one in your car. But motor oil, on the other hand, is thick and viscous. Motor oil's higher viscosity is critical to its ability to cling to internal parts of an engine and provide the lubrication to that motor. Now, what you might find particularly interesting is that these two products, which serve drastically different purposes in our engine, both commonly come from the same source: crude oil pumped from the ground. Gasoline and motor oil are both actually complex mixtures of many compounds that are very similar in their atomic composition, but quite different in the way those atoms are put together. The molecules in gasoline look mostly like this one, isooctane. They're smaller networks of carbon atoms bonded to one another and to some hydrogen atoms as well. Conventional motor oils, on the other hand, have a base which is primarily larger molecules like these, ranging in size from twice to 5 times the molecular size of gasoline molecules, and in many cases less branched. They're made from exactly the same types of atoms as isooctane, but notice they're much, much, much larger. There's a reason for that. So what is it about the structure of isooctane molecules which makes a sample of them flow more easily than one made of our larger molecules? Well, to demonstrate this, I need more than one molecule because the answer lies in the intermolecular forces within the sample. You might notice immediately that neither of these molecules has significantly polar bonds, nor do they have that essential OH, NH, or FH for hydrogen bonding. So those are some of the similarities, but now let's look at the differences. Notice that the smaller, more branched isooctane molecules can only make a small amount of contact with one another, while the compounds in oil, being larger and less branched, can form long, snug contacts along multiple molecules. This means that the London dispersion forces in the sample of motor oil are going to be much, much stronger, and this gives each component the right viscosity for their job. We can go one step further and explain why changing that motor oil every so often is so important. Motor oils don't burn as easily as gasoline because they don't vaporize as well. And the vapor phase is where gasoline can mix with oxygen to burn. Now, when heated in the presence of oxygen, motor oils can become oxidized, but not enough to cause the explosions that gasoline can. This simply means that the oxygen in the air chemically reacts with oil molecules more slowly, not exploding, but creating new molecules with very different properties. With enough heat, oxygen, and time, the hydrocarbons become what are known as carboxylic acids. Now, not only are these groups far more polar, opening the door to dipole-dipole interactions, which would make them even more thick and viscous, but they also have OH groups, making them good hydrogen bonders. And that only compounds the problem oxidation can cause. So, in time, your clean, highly refined engine oil turns into carboxylic acids, which not only can cause corrosion, but which are simply too viscous to provide proper lubrication. Now, because engines rely on heat and oxygen to run properly, there's really no way to avoid this process from taking place. And the only solution is to pop the hood and exchange the old oil for the new, beginning the process again. It's a little bit humid outside today. I hope my hair looks all right. Let's think about that for a minute. Not my hair. I just determined that's perfect. No, the humidity. Now, what is humidity? Well, of course, humidity is simply water vapor in the air around us. More water vapor, greater humidity. You might notice that in regions close to liquid water, like lakes, swamps, near the ocean, there usually seems to be enough in the air, sometimes too much moisture, right? But in areas with less liquid water around, our skin gets dry, our lips get parched or chapped, and we suddenly realize that there isn't much water vapor in the air at all. But in our lecture on phase changes, I told you that water can only boil at 100 degrees centigrade near the surface of the Earth. Even the hottest desert in the world doesn't approach that temperature. Yet, come to Washington, D.C. on an August day with temperatures in the 30s Celsius, and you will not be able to mistake the water vapor in the air, I promise you. So what's going on here? Well, the key to understanding the source of this humidity is an understanding a phenomenon called vapor pressure. Think back to kinetic molecular theory. It suggests that molecules and atoms within a sample are moving at an RMS or average velocity that depends on their temperature. But it also reminds us that the actual velocities of individual particles in the sample vary. A few are moving much faster than the RMS velocity, and a few much slower. Well, the same is true of liquids. Molecules in liquids may be packed in together very tightly, but they can still rotate and move within a sample. Now, this is what allows a liquid to take on the shape of its container, but it has another effect as well. Imagine a sample of water, something like, say, the Potomac River. Now, water molecules in that sample move at varying speeds, some faster, some slower. Now, what if one of those faster moving molecules just happens to encounter the surface of the water with enough kinetic energy to overcome the intermolecular forces holding the bulk sample in its liquid state? Well, that one lucky molecule breaks free and becomes a gas phase molecule. You might imagine that increasing the surface area would allow more water molecules to escape. Similarly, raising the temperature increases the kinetic energy within those molecules, which explains why we find so much moisture in the air here around our nation's capital every August. Now, let's look at this phenomenon from a different perspective. What if I were to compare water to a different liquid, like the historical anesthetic diethyl ether? Ether is less polar than water, and it also lacks that critical OH bond which allows it to hydrogen bond to itself. This means that ether molecules attract one another much less strongly than water molecules do. So at a given temperature, I expect more ether molecules in a sample to have the needed energy to escape the pull of the molecules surrounding it in the liquid. Now, this means that ether will evaporate faster than water. Chemists call this property, the tendency and speed with which a substance vaporizes, volatility. Now, don't confuse this definition of volatility with the more colloquial one. In casual conversation, we use the term volatile to mean explosive or reactive, but this is not what a chemist means when he or she uses this word. Instead, it simply means vaporizes quickly and easily. So in the language of chemistry, a compound can be extremely volatile and extremely stable at the same time. So now we understand the concept of volatility. Liquids with weaker intermolecular forces tend to vaporize more easily, even below their boiling points. Now, this is a handy concept to understand, but it's only what we would call qualitative. We can say that one liquid is expected to evaporate more rapidly than another, but by exactly how much? And chemists like to put numbers to properties. So let's think of a more quantitative way to measure this phenomenon. Consider a beaker filled with liquid water. We now know that a few of those water molecules can escape the liquid sample and reach the gas phase because their individual kinetic energy is great enough. If I keep that water at the same temperature, the RMS velocities of the remaining liquid molecules will redistribute and more water molecules will escape in a nice, steady process that we know as evaporation. But what if instead I closed the system so that no water vapor could escape? Now, in this new scenario, a few water molecules can still escape into the headspace of the flask, but they'll eventually, randomly, find their way back to the surface and into the liquid again. Now, as more water molecules reach the vapor phase, more return to the water until there's no net change anymore. Now, for every molecule that escapes, another one is captured, and a stable quantity of vapor is now present. If I were to do the same thing with ether at the same temperature, I would expect more ether to reach the gas phase when this balance is achieved. This is because the molecules don't cling to one another as well as water. The result of that, a higher pressure within the sealed flask containing the ether. And this pressure is what we call vapor pressure. and it gives us a solid numerical value with which to describe the volatility of any given compound. At 25 degrees centigrade, the vapor pressure of water is about 24 millimeters of mercury, or about 0.03 atmospheres, just 3% of the pressure exerted by the Earth's atmosphere at sea level. In contrast, that of ether is 0.7 atmospheres. That's 70% of the pressure at the surface of the Earth. Now, vapor pressure also changes rapidly with temperature. You can see this in plots of vapor pressure as a function of temperature for these two liquids. This is the origin of the differing boiling points of the liquids. When the vapor pressure of a liquid is equal to the applied atmospheric pressure, the vapor can now form not only at the surface of the sample, but deep within the liquid, creating the rolling bubbles that we commonly associate with boiling. When the pressure against which the solvent is working is equal to 1 atmosphere, we call this temperature the normal boiling point of a liquid, which is yet another numerical value that we can link to a liquid's vapor pressure. Now, the closeness of molecules in liquids, combined with their ability to shift and fill the shape of a container, gives them some remarkable properties, really different from gases. Not the least of these differences is their density. Because of how closely packed liquid molecules are, their densities are often thousands of times greater than the same substances in the gas phase. Take the example again of water, which has a density of 1,000 kilograms per cubic meter. By contrast, the air you breathe has a density of about 1.2 kilograms per cubic meter. That's a tremendous difference in mass for the same volume of material. And add to this the fact that liquids can flow and take on shapes of their own containers, and it's easy to see why they're often used as a means of transferring force in all sorts of technologies. Of course, one of the oldest examples of this is the classic water wheel. This brilliant invention, which relies on both the mass of water and its ability to flow as a means of transferring power to grain mills and other applications, was invented by ancient Greek, Chinese, and Indian civilizations. All three conceived this design independently. But the real magic happens when you consider not only how the mass and ability to flow, but also the fact that packing molecules so closely together makes liquids incompressible. This means that, very much unlike gases, liquids cannot change their volume in response to pressure. Instead, when a liquid is exposed to pressure, it has no choice but to pass that pressure along. This is the founding principle upon which the hydraulic press was built. In 1795, an English locksmith by the name of Joseph Bramah filed for a patent on this device. It consisted of 2 closed pistons filled with a liquid. Now, by exerting pressure on the smaller piston, the incompressible liquid inside must transfer that force rather than absorb it. And the larger that second piston is, the greater the force it will exert, in very much the same way that a lever can amplify force at the cost of travel. Back to our opening example, the brakes on your car. Now, they're not all that different from Bramah's 200-year-old invention. The braking system in your car consists of a pedal which activates a small cylinder attached to a brake line. That brake line is filled with a special fluid, which is designed to maintain the same lack of compressibility across a broad range of conditions. As you press the pedal, that liquid has nowhere to go, so it presses against the brake calipers or drum at the other end of the line. Now, being much larger than the piston at your brake pedal, those pads squeeze down with tremendous force, enough to literally stop a speeding car in its tracks. This is why it's so important to change our brake fluid every so often. As that fluid decomposes or takes on water, its chemical properties change, and small bubbles of gas can begin to form inside. Now when you press on the pedal, those bubbles actually can change their volume and absorb that force. And this, of course, is bad news because the force is no longer being transmitted as it should be. This results in soft or even non-functional brakes. And automotive braking systems aren't the only important application that exploits this property of liquids. Let's take a look at another very important one right now. Well, after a hard day of recording demonstrations in the kitchen, I always like to unwind with a glass of wine. So I've got my wine here and some glasses to enjoy it in, but something's missing. A cork. I've got to get the cork out, but I don't have a corkscrew. Now, what do I have that I could what other tool might work?
Of course.
Shoe. Now, most of us are familiar with this little parlor trick of opening a bottle of wine using a shoe, and more accurately, a shoe in a very sturdy wall. But what you may not have thought about is that this little trick, which does in fact work, is an excellent demonstration of the difference in the phase behavior of liquids and gases. Because trapped inside of this bottle are two things that I'd really like to let out. First, this little bit of headspace here, but more importantly, the wine on the inside that's in the liquid phase. So I have a gas and a liquid trapped inside. If you've ever seen a video of someone accomplishing this really interesting feat, you'll always notice that they tend to tilt the bottle sideways and hit the bottle against a wall using a shoe for cushioning to avoid breaking the bottle itself. And you may have asked yourself, wouldn't it be easier to let gravity do some of that work and simply bring the bottle straight down onto a hard surface? And there's a very good reason why you never see it done this way. The reason comes down to the difference in the behavior of two phases, liquids and gases. You see, gases contain molecules that are spread out by great distances and aren't really touching one another. As a result, if you try to compress a gas, its volume simply changes. But liquids are different. In the liquid down here where the wine is, all of these molecules, the water, the ethanol, all of those delicious esters and other flavor compounds that are inside are practically touching one another. So when you compress them, they have nowhere to go but bump into one another and create a sort of a shock wave that can move through the liquid. The act of banging a bottle against a hard surface creates a little pressure wave that travels through liquids, but when it reaches gas and those gas molecules aren't touching anymore, that pressure wave is lost. And so, banging the bottle straight down is akin to trying to pump the brakes on your car when you have air in your brake lines. There's simply no force being transmitted where you want it to go. But notice, if I tilt the bottle on its side, that the headspace gas has moved up into the top of the bottle. And now the point of impact with the wall and the cork that I want to remove are all continuously connected by liquid. So that means that any force that I create here in the form of a shock wave is going to move along the bottle and eventually affect the cork, hopefully expelling it so that we can call an end to this day and enjoy a little bit of what's inside. Yet another property of liquids that is of importance is the concept of miscibility. Now, we can think of miscibility as a description of how well one liquid dissolves into another liquid. Again, contrasting liquids to gases, we always assumed in our previous lectures on gases that each gas would uniformly take on the entire volume of its container. This would mix them thoroughly with all other gases regardless of their identity. But just as in our previous segment, liquids are going to be set apart by the fact that molecules in liquid phases are very close together and they interact with one another very strongly. Sometimes this interaction is favorable and sometimes not so favorable. This concept can be observed quite easily in the aisles of your local grocery store. But let's start with an example of a favorable interaction. Water and beverage alcohol, also called ethanol. Right? They look somewhat similar at the molecular level, don't they? Both are polar. Both have the critical OH bond needed for hydrogen bonding. And both are fairly small in size. What this means is that water and ethanol molecules can interact with one another almost as strongly as they do with other molecules of the same type. So when mixed, they blend together to form a single uniform mixture of alcohol and water. But what happens when we try the same experiment? But this time, let's use something else. Let's try motor oil and water. Now, motor oils are usually a complex mixture of compounds, but they're all of similar chemistry. They're those large molecules consisting of mostly hydrogen and carbon with very few polar bonds and very little hydrogen bonding capability, if any. Now, instead, motor oils are held in the liquid phase by powerful London forces generated by their immense electron clouds. So, if the molecules in my motor oil want to stick to others based on London forces, But water is held in the liquid phase by dipole interactions and hydrogen bonding primarily. How well do we expect water to interact with oil? Not well at all. The oil and water would rather cling to molecules of their own kind than to one another. The result is what we call a biphasic liquid, one in which there is a lower polarity oil phase and a higher polarity water phase. They simply won't mix because they don't interact well. This is one of the reasons why you don't want to release motor oils and products like them into the environment. Their immiscibility with water causes them to form concentrated films of oil that can float along the surface of natural waters, disrupting ecosystems that they pollute, rather than simply dissolving into groundwater and being carried away. So the miscibility of liquids tends to improve as the molecular structures of the compounds making them become similar. Like dissolves like. This is why you can mix gases and oil to get the two-stroke motor running on your weed whacker. Or you can combine water and antifreeze, a compound known as ethylene glycol, to fill your radiator. It's also why you have to shake your vinaigrette before dinner and pour it quickly before the layers of oil and water are able to separate from one another. And it's also the reason why cleaning up oil-based paint with water is a losing proposition, but turpentine takes it away with a quick swipe. So let's summarize today's discussion on liquids. We started with a quick review of intermolecular forces, reminding ourselves that all the same forces from our gas lectures would come to bear on liquids, but with even greater influence since the molecules in the liquid state are so close together. We discussed the concept of viscosity and how stronger intermolecular forces create resistance to flow. Then we talked about volatility and vapor pressure. We discussed the common confusion encountered when the common definition of volatile is used and how chemists instead use the term to describe liquids that vaporize easily. Next, we tackled compressibility, or more accurately, the incompressibility of liquids. We saw how this makes liquids a perfect choice in devices which transmit force, helping you to stop your car with a tap of your foot, or even open a wine bottle in a pinch. And finally, we discussed miscibility and how liquids of similar polarity, molecular size, and hydrogen bonding capability are better able to mix with one another. And with that, we finish our introduction to the properties of liquids. Our next task will be to finish the trifecta of phases by getting familiar with some of the general properties of solids.